All right. So my favorite part, that was the song we played before the lecture. Like today is one of the lecture I like the most in CS203. Guess what's my least favorite? The first part of the last lecture. Because I hate everything that's only talking about like hardware design or something. That's boring, right? I hear you. I'm a CS major. So but right now, let's come back here and see what's going. Why are we talking about this matrix multiplication as a case study in this? It's because like latency between CPU and DRAM is so significant, become a huge performance gap. And to mitigate this performance gap, what we have been doing is that on the hardware side, we built memory hierarchy. However, even with memory hierarchy, there are three reasons make this cache that less effective. First is compulsory misses, because the first time you access a block is always a miss. And the second case is capacity miss. It means that the working set size of an application is bigger than the cache size. And then, even though right now I tweak my code or I tweak my application, or sometimes I just have smaller data set, I still see a lot of misses. That's probably because you are meeting the issue of conflict misses. So like every time when we ask you to analyze what's the cause of the cache misses, you cannot forego the other two before you talk about this is conflict misses. And for the capacity misses, you also cannot forego the compulsory misses before you talk about it. So if you see like in AutoGrader, it talks about like, oh yeah, you didn't discuss the relationship between capacity and the cache misses, is probably because first of all, you didn't mention the word capacity misses at all, or in your discussion, you never cite your working set size, you never cite how many elements has been visited between this point and this point, you never talk about how many bytes are there in your cache capacity. How can we consider you as a good discussion regarding this capacity misses? A lot of people are complaining to our TAs about like, okay, the AutoGrader doesn't work very well for me. Well, it doesn't work very well for you because you didn't give the AutoGrader or like us the answer you want. One thing I can tell you is that there was before I started using this AutoGrader, the average grade of assignment was 67. And after we start doing that, the average grade of assignment become 80 something. So like AutoGrader is more relaxed on grading already. If you give a real human TA doing that, I don't think you are going to get as better grade as we are right now. And the other thing is that you only have one shot, but right now you have unlimited shot. So I would say like focusing on, instead of tweaking the AutoGrader, focusing on did I miss any like big stuff, because that's all what we have been testing. Like a lot of you, well, getting answer wrong because you never like respect the format of answering the question as I told you in the class, right? And this is my class, how can I give you correct answer, right? So like how do you tell, right? So importantly, list the cache geometry through C equal to ABS, and then list the memory accesses that you have in this pieces of code. And for each access, you can pretty much tell what kind of cache misses that. You don't have to list all of the cache accesses, but you have to list some of this to show people, yeah, as you can imagine, this is going to repeat again and again, right? So other than that, so after we figure out what's the cause of cache misses, we have been demonstrating mechanisms to improve it. Hardware mechanism, as I told you, I'm not super excited about those because most of the time you won't get it or you already have it. I'm focusing more about, as a software engineer, what we can do. So 3 things that we have been talking about the last time regarding how to optimize our loop. Loop interchange, meaning that we can change the order of traversing the loop to improve the locality of data accesses. And loop fission, meaning that we are splitting a loop into 2 so that we can improve the potential conflict between your data accesses. Or if you are having a processor with many ways associativity, it doesn't hurt to do loop fusion because don't forget, instruction count still matters, right? So if you split stuff into 2 separate loops, why we don't want to do that? Because you are going to have more instruction count. So today we are just going to talk about one thing called matrix multiplications and how we are going to optimize for matrix multiplications. So before we start, why do we care about matrix multiplications? Can you talk to people around you? All right, why do we care about matrix multiplications? Why do we care? Render video games. So what kind of rendering algorithm do you have in mind that would use matrix multiplications? So rasterization is actually use vector, and for ray tracing is a pretty irregular case, and it's more like a serial process that doesn't really need like a matrix. So I wouldn't put this 2 in the picture. What else? Neural networks, right? So right now, everybody is talking about matrix multiplication. If you can optimize matrix multiplication, you can pretty much like optimize the neural network training, right? Like, wait. You should have known this, right? Like in your programming assignment 1, what's the most time-consuming function? In the backward propagation, matrix multiplication, right? And in fact, for the forward propagation, there is also a matrix multiplication function, and these 2 together is account for like 40% or even more amount of time, right? So in neural networks, like matrix multiplication is very important, right? If you don't have this on top of your head, I would probably doubt if you really do the programming assignment yourself, right? What else? What else? Okay, so in fact, matrices are everywhere. Like graph algorithm, every graph, there is a theory called matrix semi-ring. you can use matrix multiplication to solve almost every graph problems. Relational database operations, a lot of us are right now using like hash join or some kind of other like algorithm to solve this database operations problems. But in fact, those are pretty much could be considered as sparse matrix multiplications, right? Like language recognition, like hidden Markov model, those are based on matrix multiplications, right? So you can imagine matrix multiplication, they are pretty much everywhere. And even for scientific computing, matrix multiplications are everywhere, right? So that's why long time ago, like 30 years ago, 40 years ago, there are already like C+ libraries or a lot of BLAS libraries try to optimize for matrix multiplication because it's really essential in a lot of scientific analysis. So today we are going to talk about this matrix multiplication. But before we talk about matrix multiplication, first of all, in C, how do we actually implement a matrix? So in fact, if you learn sufficient enough stuff in C, you will know that there is not really a data structure called matrix. And in fact, there is not really a native matrix data structure because if you think about the memory space we have, basically everything is linear, right? So if it's linear, it means that the data structure should be mapped to just 1D. So even though we declare a 2D data structure or 3D data structure, it's always the case that the language has to remap it to a 1D data structure. So what it turns out is that if you want to allocate a matrix and internally, or what you have to do is that you need a two-step, two-level memory allocation. So saying that if I want to have a two-dimensional array, you have to declare a double pointer. So for the double pointer, the first level, when you do malloc, pay attention to this. We are doing size of a pointer. So the reason why it's size of a pointer because this first level is an array of pointer. So what does that mean is that in your top level data structure is basically not really storing the real data. It's just an array of pointers. And internally, you are going to separately allocate an array of like rows or columns based on your orientation of your language, right? So what happens here is that I declare the first level index as the row, and then I allocate the space for each row, right? So that's how C does things. And for Fortran, they do things completely different. The first level index is column, and the second level index is row, right? So what does that mean is that high levelly, your abstract, you think I have a data structure like this, but in fact, the physical implementation is for the A, the double pointer itself is an array of 4 elements, and each element is just a pointer to the beginning of a consecutive space that stores a row. And if you consecutively call malloc, by default, it would allocate consecutive memory addresses for you. So that's why most of the time you can pretty much imagine it will be stored one row after another in the virtual memory address space because that's how malloc does things in general. There are definitely exceptions. For example, if I made my program multi-threaded and if there are other threads in the middle interrupting this malloc, then it could potentially be disjoint. However, conceptually, it should be one row after another. That's how C implements the two-dimensional array. So you can imagine like an Aij, you can also access them through a one-dimensional way that is Ai times n plus j, right? So this kind of, this will work. So let's talk about this. So for matrix multiplications, this is the concept saying that I have a C, which is the result. The dimension of the C is m times k. And to get this m times k array, what I have is an m times n and n times k as the input array. So based on that, it's probably not too difficult for you to imagine. This is the 3-level nested for loop that I'm going to write. So I think you guys are wise. So can you guys tell me what's the complexity of this algorithm? M and K, or say n cubic in general, right? So what does that mean is that, okay, so what does that imply? So if I have M and K as 1K, and I say like it takes about 2 seconds to run this, can you tell me, can you like estimate how much time it would take to run for 2K by 2K by 2K? Like 1K by 1K by 1K takes 2 seconds. How much time do you think 2K by 2K by 2K would take in theory? 16 seconds? All right, 16 seconds, right? So that's what we would imagine. But what's the reality? You know it's not going to be the same as our imagination, right? So now let's run it. So first of all, this is the exactly the same matrix multiplication code that I put on the tape. Oops. Hello. Is it okay? What happened? Give me a second. Let me see what's going on here. Okay. Not working. Why? Okay, give me a second. Let me check real quick. Okay, seems like the hello. Here we go. Okay, so let me do this and see what's going on there. Still doesn't run? Really? Log out and log in. Okay. Why? Why? Tell me why. Okay, let me see if this way would it work. Matrix small. No? Okay. Something wrong. Okay, give me a second. Okay, here we go. Sometimes restart, solve everything. So right now, let's run this. So this is the matrix multiplication, and I'm going to run it with different sizes, and let's see if that goes with the theory of computation. So Um, Okay, so the first two, they run pretty quick, right? And now we are still waiting for other result to generate. And as you can imagine, it will take longer time. But so from here to here, it should be 8 times longer. From here to here, we imagine it to be 8 times longer. So finally, it generates something, right? And then we are still running, waiting for another, which is 4K by 4K to run and see if any of this will follow the theory of computation. And turns out what we have here is this. So let's see. So if you check the result, you will see, well, first of all, one like for the 512 by 12, 512, it takes 0.13. And for 1K by 1K, it takes about 2 seconds, right? So if you times this amount by 8, is it around 2 seconds? Not really, right? Because it's supposed to be like 1 second or something, right? So you know, like even between 512 to 1K, it already breaks. And for this 2 to like 1K to 2K, right? We are supposed it go from 2 to 16, but it actually goes to 21. So it means that there must be something else disturbing the execution of the code, right? So another thing that you can pay attention is that if you put some efforts in analyzing the instruction count, the instruction count is pretty much following the 8 times difference, right? So what does that mean is that computation theory is correct in predicting the increasing in instruction count. But what really different is you see the CPI, it jumped from 0.6 to 1.32 to 1.75. And the reason is because we have pretty high cache miss rate. So why is that? And what kind of misses we should address the first? All right, let's take a look. So the initial votes shows that, wow, very diverse answers. So why don't we have a discussion among you guys and see if you guys would reach a consensus. All right, let's take a look. So after discussion, okay, it looks like E is a more welcoming answer. And A also is the second most. So most of you believe compulsory misses and conflict misses are either compulsory misses or and conflict misses are the most majority. Why is that? How do you judge?
We were slowly going through the process of trying to find the working set size
Mm-hmm.
and the cache capacity size because that could help us immediately rule in or out capacity misses.
Okay, so regarding this case, what do you think would be a reasonable period of time that we should observe the working set size? Saying that which data structure are we revisiting sooner? So look at the way how we perform matrix multiplication, right? We are multiplying a row of to a column, right? And then what do you do? Do you increment J first or I first? You increment J first, right? So A is probably going to, the same element in A is going to be revisited faster. Do you agree? But for J, we are pretty much going through, KJ is going to be revisited later, right? Because we are consistently changing the JK before we changing the I, right? So what does that mean is that we will revisit a row first, the same row first. So if that's the thought, when I revisit the row, how many data have I visited? This single row. And what else I visit? What else did I visit? Between the last visit of the first element of a row and the next time we visit the first element of a row. How much data we visited? That's the working set, right? How big is that? What? Is it only 2K? How many? Right? Before you come back, how many are you going to visit? So how many? Is it 4K? 2K squared, that's 4M. 4M elements. How big is each element? If this is double. If you have to visit 4M elements, each element is a double, how big is this working set? Is this a very difficult question? How big is an element? A byte. How many elements are we visiting? 4M. So what's the answer? 32 what? 32 megabytes. How big is our cache? How big is our cache? So what type of miss? What's your answer? Most of you pick A and E. Compulsory misses, conflict misses, but you guys don't ever think it's capacity misses. But the answer is indeed capacity misses. So that's why I'm saying when you solve this question, don't forget to check capacity misses first. Very likely there will be capacity misses, right? So again, look at the code, right? If I want to count Cij, I will first visit like AI and the column of Bj, right? And then I would, if I want to count like Ci plus 1 and J, then I would do is, well, so the next time I would do this, I would do like AI times J plus 1, J plus 2 until I do another, right? So you can see each row, how big is each row? Each row is already 16 kilobyte. I only have a 48 kilobyte cache. You don't have to visit the whole B. Only 3 columns or 3 rows is going to kill you. Do you agree? Simply this is going to kill you. So there's no reason why it's not a capacity miss. Right? The first access, I believe. But the thing is that we have to reuse A again and again. And every time later on is categorized as capacity miss. Because between we revisit the same row, it already has tons of capacity misses, right? So since your working set is so large, it's unlikely that you can keep any of this in a cache later. So that's why it's always a capacity misses later, right? So how do we deal with that? If we only have 48 kilobyte of cache, how do we deal with that? So the first issue is that, right, if we want to reduce cache misses in matrix multiplication, first of all, the most major issue we identify is that we have capacity misses. So if you want to reduce the working set size, right, we should try to see if we can reduce the amount of data we visit before the next revisit of the same element, right? So that's the idea, right? But back to that, capacity miss is the answer to this one. It's not A, it's not E, right? So this is indeed a case of capacity miss. So how do we deal with that? How can we reduce the length of, how can we reduce the working set size without affecting the correctness of the result? What? How do you split the matches? Okay, here we go, right? So mathematics matters, right? So in the very beginning, I briefly talked about matrix semi-ring, and actually, like there are several papers we published are based on matrix semi-ring theory, and I really love matrix semi-ring theory. So if you find there are other usage of matrix semi-ring theory, feel free to talk about that. But one beauty thing about all the matrix semi-ring operation is that they all share this property, is that if you pay attention to the format of matrix multiplication, each Cij is essentially the sigma of Aik times Bkj. You will feel like, okay, what does that mean to me? So now, if I break the sigma into 2 segments, for example, I change the boundary to just like 0 to 2 to n and 2 to n to n minus 1, I can actually split this operation into 2 several different parts. And as you can see, when I compute on each part, I only need to visit the half amount of data that I would need compare against the previous, right? So what does that mean is that you can continuously expand this theory. Let's break it down into quarters or even more, as long as this would fit the working set size of your cache, right? So this is, so graphically, what does that mean is that instead of every time I compute the result all the way to the end, when I compute Cij, I don't, the first step is that well, I only compute the first sigma, right? So right now I'm showing a case that I break it up into two, right? So first of all, I don't go all the way to the end, right? I only go to half of them, right? And then now I move to the next Cij, and then I visit another one, but again, I don't go through them to the end, right? So you can see every time I only do like quarter drop, then the past, right? And before I go to this boundary, right, of the C, I instead directly move to the next element, right? So what does that mean is that with this, what will happen is that every time when you run this, you only need to visit limited amount of elements as the past, right? So in this way, you are reducing the working set size, right? So you might wonder, okay, so in this way, right, you are going to kick off all the capacity misses, but only compulsory misses are left if you do things right, right? So let's say if we can break up this matrix multiplication into different segmented sigma, right? Then, and okay, so like the same thing, right? You can keep going on, so then you can compute the lower tile, and then like you can continuously reuse this tile, right? And as you can see, if you consider this part, your cache miss rate would be even lower, right? And when you want to, of course, there are still like some of the cache misses that we are going to suffer, right? And now, if I say I want to finish up this computation, right? Then again, this A, you can move to another tile, but in the meantime, because I have done everything I need for this tile, so I don't care about this part anymore, and I can focus on finishing the rest part of them, right, in the future, right? But every time when I perform this quarter by quarter operations, there won't be any capacity misses, right? So that's the trick, right? So this is the idea of tile matrix multiplication. So if I want to do this tile matrix multiplication, you can imagine this is how I'm going to code, right? So in addition to this 3-level nested loop, I need to have an outer loop that would help me partition the original matrix into tiles with the tile size that I selected. So with the right now, right? Think about this. In our cache, we have 48 kilobytes. What's a right tile size that you would think good for the capacity we have? Right, so let's do an easy calculation, right? Like you can have most like 16 kilobytes for each matrix, right? So if you take a square root, it will give you 45, but you know, like we like things to be 2 to the something, right? So the 2 to the square that doesn't surpass 45 is actually 32, right? So why don't we pick 32 as the size we want, as a tile size? Do you guys agree with that? So with 32, we are not envisioning any capacity misses. Do you all agree? Because each time when I perform operations on the tile, we do not go over 16 kilobytes, right? Okay, let's take a look and see how does that help. So right now, we have this block matrix multiplication. And here's the code, exactly like what I showed on the slide. And now I'm going to remake the program again, so you know that I'm not cheating. And let's try when the tile size is equal to 32, and let's see how does that play. So it would take some time to run because I'm going to run quite a few different sizes of the matrices to show you something. And when I display the result, I will also reference the original non-tiled version of the matrix multiplication as the baseline. So then you can compare how good are we in doing this, right? So Several things that we would imagine to see after this result has been finished, and it actually takes pretty long. Is it everything working correctly? Sometimes I doubt about that. Oh, okay, here we go. Okay, so first of all, the upper side should be the result that you are familiar with already. The execution time, let's focus on this 2K by 2K case because that's the one that we seem to be more problematic, and that's the one that I asked you in a question. So if you look at the 2K by 2K, it was originally 21. But now, if I use tile size as 32, how much time it takes? It goes from 21 to just 5 seconds, right? More than 4 times speed up with three more levels of the loop, right? Isn't that amazing? Right? And if you look at the cache miss rate, it goes from 30% to 21%. Really? 21% miss rate still? Why is that, right? First question. And but as you can see, right, even though the miss rate doesn't seem to reduce a lot, but right now the CPI, cycles per instruction, is actually reducing a lot, right? It was originally like 0.65 with the with non-blocking version, but now it's 0.35, right? And another thing that was noting is if you compare the case between like 1K to 2K, they are pretty aligned with the algorithm complexity estimation for 8 times, right? And even for 2K to 4K, right? It's about 5 and this is about 40. So we are pretty much roughly about 8 times. So computational complexity works well in an environment where you have relatively low cache miss rate, right? It also means that cache miss rate is indeed, cache misses is indeed the most important factor in affecting the CPI, right? However, are you satisfied with this? It still takes 5 seconds to count on this. Are you satisfied? Okay, you have to say no, right? Otherwise, how do I spend the rest 40 minutes, right? So the answer is no, right? Because we still have this 21% high cache miss rate. The same question that I'm asking, why we are still seeing 21% of the cache miss rate in the remaining code? All right, let's see. Without discussion, oh wow, there are 3 answers that are pretty popular. So why don't you guys talk to each other regarding A, C, or E? Ace. I like this. Ace it. All right, let's take a look of what you guys have after discussion. Okay, so it seems like it's either A, C, or E still. Some of you start to think, is there any capacity miss remaining? Okay, so for this kind of question, again, when we ask you about what type of the misses are there, okay, first of all, tell me which type of misses is the easiest to count the number of them. Compulsory misses, right? So for these pieces of a code, how many compulsory misses are there? So how big is our matrix? So it's, first of all, a few observations. We are going to visit each element in each of the matrices for at least once. Do you guys all agree? Right? So how many elements are there in total? Three times 2 to the, this is 11, right? 2 to the 11 square, right? Divided by 2 to the 3 because it's 8, right? So this is going to be 3 times 2 to the 19, right? How big is this? This is like 2 to the 10 is what? 1K, right? So this is about like say 2 to the 20, right? About 1 million, right? Okay, now let's go back to the previous stats that we have. How many cache misses are there? Okay, so 1 million. And we are looking at 2K, right? How significant is 1 million here? So this is the total number of L1 cache misses, right? 1 million is 160, right? How many more digits do we have? 4 more. So it's about like 1 over 10,000. Can we say this is the major type of miss? Okay. And another thing that we learned, right? Oh, sorry, this one, right? So this case, right? Okay, even for this case, right? It's still like 1 over 7,000, right? Still ignorable, right? Negligible, right? So this is not major at all. And we know, since we already tile the matrix perfectly, is there going to be any capacity misses? Right? The working set size right now is set to 32 by 32. Less than 48K. Right? Compulsory misses, they are not major. And capacity misses should be 0. What's the other type of misses? Conflict misses, right? So now, if you pay attention to this, right, the answer is crystal clear that only conflict misses should be the answer. There are compulsory misses, I agree. But 1 over 7,000, what the question is asking? Majority? It's not majority at all, right? It's not, it's minority, 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 right? Right? So, but the thing is like, why do we have conflict misses still? So let's take a look, right? So now, if you think about this, right? When we traverse, the way how we write a code, when we traverse B, right? What happened is we are going to increment a K, right? KK, right? So the first one you are going to access is B00, B10. B20, B30, B40, right? So if you do C equal to ABS, and let's assume a starting address, right? You can assume any consecutive starting address in your memory space. You will always get the same result, I promise you, because that's the theory in math. And you partition, you will find out with 2K by 2K as the size, every column, they are going to share the same set index in the cache. So what does that mean? When I visit B00, I fetch a block into index 0. B10, I fetch another block into index 0. When I add B11, I fetch another block into index 0. So at this point, I already have 12 blocks of B in index 0. How many way associativities do we have? 12. So what happened when we try to access B12? Well, at this point, it's not conflict miss, but I will kick out B00, right? But what's the conflict coming from? When I come back and visit B01, it will become a conflict miss, right? And there are 7 other elements in each B, or well, sorry, 31 other elements in B that I have to visit for the tile matrix multiplications, right? So in this case, the working set is indeed smaller than the cache size. However, I still see those misses. Where are they from? Conflict misses, right? That's why you have conflict misses, right? So what does that mean? What does that mean? 32 is not a good size, right? Because if you go to 32, it's over 12, right? So if we want to deal with this situation, what do you think would be a good tile size to pick? Something smaller than 12, right? So let's say, what if we do 8, right? So what if we do 8, right? So let's try to see this demo to see if 8 really helps us a lot. Now, this is 32 right now. Let's run it with 8. Oops. Not finished yet. Shouldn't be finished this. And in the meantime, I will consistently run other cache sizes so then we can see how different cache sizes interplay. So for tile size 8, I'm also going to test different matrices size, so you would have a side-by-side comparison with those blocking algorithms, and we can take a look and see if tile size equal to 8 really improves a lot. So now again, this is quite a large set of experiments we have to run. So as you can see right now, with tile size equal to 8, what happened? So look at this, right? The execution time for 2K by 2K by 2K now is at 3.27, and it was originally about 5, right? So we do see a significant improvement. And the other thing is that pay attention to the cache miss rate. It was originally about 30%, right? And the reason why it's 30% is probably not too difficult for you to imagine, because for for C and A, we are not going to see a lot of misses, but for B, it's always a miss, right? And it's 1/3 of the memory accesses. So that's why you see a 30% cache miss rate. So that's a pretty reasonable number to see. But now, if we tile it by 8, we are only seeing 0.01 as the miss rate, which is very, very low, right? Only 1% of the cache miss rate, right? Okay, but now let's keep running some other tile sizes, and let's see what's going on. And as you would see is that, okay, with different tile sizes, we do see different runtime. So remember, for this 2K by 2K, we had 3.22 with a tile size equal to 8. And then for 16 is 3.37. And for 4, right? Some people might think, what if I go below, right? Then you will see like 4.4, right? So the tile size 8 is actually like pretty optimal, right? And if you go to 32, this is the previous case we have, and go to 64, right? It actually goes large because you are now having capacity misses coming back, right? So, and as you can see, right, when you go larger, right, your catch miss rate is pretty much staying at the previous, pretty close to the previous case that we don't have tile matrix multiplication, right? And pay attention to the miss rate, right? The miss rate of tile size equal to A is indeed the lowest among all, right? So this is an evidence now we found the optimal tile size. However, sometimes, so we are just lucky because sometimes when I run this experiment, I don't always find 8 as the best size. So this is the experiment that I just ran before this lecture. So like this morning when I ran this, you will find out, well, 8 is not the best size. In fact, 16 is the best size. However, you might argue, right, why 16 is the best, give us the best execution time, even though its cache miss rate is 7 times higher than tile size equal to 8. What's the other factor that you think would affect instruction count, right? Because if you pay attention to that, the CPI of the case where is 16 is actually higher, but slightly higher, just slightly higher, right? However, if you count, if you pay attention to the instruction count, it's actually increasing more than the improvement of the CPI. So a lot of times when people are optimizing code, they only pay attention to the cache miss rate and they thought cache miss rate is everything. However, one of the things that you have to be really careful about the tiling is that don't make the loop overhead go over the benefit you can get. And if you haven't get a chance to visit programming assignment 2, it's probably not too difficult for you to imagine what are we going to do. You are going to apply tile matrix multiplication to modify, to optimize this mat-mul backpropagation. However, if you try to use ChatGPT or other generative AI tools, I have tested Gemini and ChatGPT. They do tile matrix multiplication, but the code they give you won't work. I mean, by won't work is that it just makes you slower, right? So like if you really have no idea, like maybe just submitting the baseline code will give you higher grades than ChatGPT, right? But on the other hand, what I really need you to do in this programming assignment, you have to use all the mechanisms that you have to learn, you have learned in this class to make it better performing than the baseline, right? And by the way, the baseline, as many of you might be aware, is already a released code on GitHub. So it's already optimized. So you are trying to optimize something that's already optimized. So that's very difficult. If you haven't started, good luck. All right, so, but instruction count is indeed into play here. So the second thing, the second takeaway here is that we need to ensure appropriate tile size will not lead to conflict in sets, but also be careful about the increasing amount of loop. And the other thing that I want to say, there are still rooms of optimization. So if you have spent time in assignment 2, you should be aware that most of the time, if you are, the one thing that compiler won't do is that if you are writing code in this style, each of this would become a memory access, right? They don't actively put things in a register. So as a programmer, you have to really think about what are the things that we can do to reduce the memory accesses. So if you pay attention to what was there, you can think, you will figure out that if this is the outer 2, right? If this is controlled by the outer two loop, then you know like for quite a while, we are not going to touch a different Cij. So one thing you could do is that you could put another variable to store the temporary result and put it, accumulate that to Cij at the very end, right? So you only incur one write accesses at the end, right? But then the other iterations, you are not going to access C at all, right? So this would also help to reduce the data we have to fetch for C each time. Slightly help in capacity, but capacity is right now not a big issue, right? So you might think, okay, this kind of trick, how does that help, right? So let's see how simply making making stuff in register, which is the code that we see here, would help. So now, let's see. Let's run this. Like right now, the experiment that I'm doing is that I just put everything, all the intermediate result as a temporary register in accumulation, right? To reduce the amount of memory accesses and see how would that help us. And remember previously for 2K by 2K, the best we got is probably something like a 3.3 seconds. And so now it's a time that we can see with different block sizes, how good are we? Oops, forgot this one, okay. No, are we going to run it again? Okay, sometimes this has to be rewritten. Okay, what if I do this? Okay, so now let's take a look. So with things in register, how much time are we taking? It's only 2.57, right? Isn't that a magic? Another thing that's also interesting, what's the best tile size now? 16, right? So why is that, right? The reason, again, is because now the instruction count matters more, right? Because with fewer amount of memory accesses, right, the instruction count becomes a more important factor. But now I'm going to do something that increases the instruction count, called matrix transpose. So with matrix, so previously, we have the issue that you remember, right? We do have the conflict misses because when we access B, it's column by column, right? So this caused all the conflict misses. And the other thing is that you will see that because they are traversed in different orders, so the locality of this column access is really bad, right? So why don't we add one piece of the code in front of the matrix multiplication to transpose that matrix, and then when I count the result, I do it on the transposed matrices. So both of them are now traversed in a row order, right? And now let's see, how would that help? So this is similar to the sorting that I introduced, right? Now I'm adding more code transpose before the matrix multiplication. And let's see how much time it would take. So now let's see how much time it would take. Oh, shoot. Here, I think I accidentally rerun the baseline matrix multiplication again. And also, like with the transposed version, you can also apply the register optimization that we have introduced. And let's see how much this whole thing would help improve. Okay, so first of all, let's see the pure result of using transpose. So as you can see, right? With transpose, we does increase the instruction count, but previously the runtime was about 3 point something, right? But right now it's below 3. And for the cache size of 16, it's even lower. It's only 2.46 now, right? And the other thing that worth observing is previously, if you pay attention, the cache miss rate of 16 was about 7%, but it's now going down to 2%. So something else is happening, right? And even for the cache size go beyond 16, everyone's cache miss rate is pretty low at this moment, right? So that's why you see even for tile size equal to 64, we are getting 2.48 seconds, right? They are all pretty close. So what does that mean is that transpose, it does increase the instruction count, but in a good way that we are changing some kind of misses. What is that? All right, let's take a look. Okay, so most of you pick C, but why don't you guys discuss with others to see if it's, why is it C? Is it really? All right, let's take a look at this case. Okay, so now more of you think it's conflict misses, so I want to hear from you. Why do you think it's conflict misses? Improve the spatial locality, but more theoretical perspective, like through the theoretical analysis, what do you think? Are we going to reduce the amount of blocks that we visit? So are we going to change compulsory misses at all? Not really, right? So compulsory miss is not improved at all. So, but how about capacity misses? So it was tiled algorithm. So first of all, I want to say, I just figured out that I didn't define this question very well. depending on the tile size, right? If your tile size is greater than 32, you are still going to have capacity misses. So, but if you talk about capacity misses, would this help? Maybe not, because you are still going to visit the same amount of data, right? However, by changing the orientation from column to row, you are going to improve conflict misses for sure, right? So the answer to this one is definitely improving conflict misses, right? So with transpose matrix multiplication, right? Previously, we are traverse in the column order. However, right now, if I am consistently performing on this part of multiplication, in the past, I would have to fetch the lower tile because that's the rest part of the matrix, the B matrix, right? However, for now, all I need to do is that I can consistently go further. And because so if you pay attention to this, we said for different rows in B, they are going to conflict in number of sets. However, if we keep going, that's typically not the case. Because for consecutive addresses, they are typically going to be a different set index, right? But if you jump it row by row, it's very likely to create conflicts. So if you change the orientation from this, it would help remove those conflict misses. But another implication is what? Remember, the current tile size that we pick is 8. That's fairly small working set compared against the whole cache size. So with the transpose, another potential we can go is that we can actually go further. We can actually go further, right? And if you use the register, you can actually kick out the space that you need for C, right? So what does that mean is that you can actually use a larger tile size for this transpose matrix multiplication, still maintain low cache miss rate, but also a lot lower instruction count as well, right? So what does that mean is that transpose really improve the behavior. So let's take a look. If this is the previous run that I have this morning. So before and after transposition, you can see the best performing configuration among those go down from 3.5 to 2.46, which is pretty similar to what we have. And the other thing that you might have mentioned is that the best tile size now can be changed, right? So previously it was 8 or 16, but now it could be either 32 or 64. Why? Because when we go further, they will still fit into the cache, right? So if that's the case, right? And if you and the cache miss rate goes really low, right? So transpose, it sounds like we are adding some overheads, but it actually improved the miss rate a lot, right? And if you can, together with the optimization in registers, it would actually help going down the execution time further. So another thing is that, right? Remember, the reason why we have conflict misses is because we are visiting more rows at a time, right? But if we keep going through the same row, they are not going to be overlapping in the same set index. So what does that mean? The best result of the tiling algorithm is not squared tile. You should actually have rectangular tile so that your row, the span of your row, still within the setting, the set associativity you have. And the width of the tile that you visit can still fit into the cache capacity, right? So if that's the case, right, well, all what we need to do is that we want to make it rectangular. So right now I'm going to run, for the sake of time, I'm only going to run this, is this the, okay, so this is already the version with the rectangular and with register optimization. And let's see what's the best we can get for now. So again, right, as you can feel, like physically feel, every time right now we are producing the result in a much faster rate than we used to have, right? In the past, we always have to wait, and I'm like a stand-up comedian that always have to think about, okay, what are the jokes that I have to say, but because I'm not so talented, but this time I don't even have to finish the sentence, right? So with different size, you can see, wow, what a magic. It's only like 1.68 now, a lot lower. And if you check the size, 32 by 8, this 8 is smaller than 12, right? And this 32 is actually ensuring it fits into the cache, right? Remember, we have the square root as 45, right? So 32 fits into the cache, 8 within the capacity. And if you go up to 64, it's actually not that bad, but it's also very close, right? So what does that mean to you, right? We are actually bringing down the time a lot, right? Now matrix multiplication can be done in seconds, just 1 second, right? Best performing at, well, so previously it was 32 by 16, but now when I do it, it's 32 by 8. So this is very small change, right? But yeah, but as a summary, here are the software optimizations that we have learned so far, right? Data layout would help reduce all 3 types of misses because we are basically reducing the working set. Loop interchange or data layout can also change the way how we traverse, right? So for example, matrix transpose is a technique that changes the layout. It helps us to reduce the conflict misses as well, right? And for loop interchange, it helps to improve the conflict misses, loop fission, try to reduce the loop fusion, try to reduce the, what I want to say. So try to reduce the memory accesses. And for blocking tiling, in fact, we are improving the cache capacity misses and conflict misses. Okay, so right now you are seeing, are we done? There are still 1 type of misses that we care about, right? So that's called compulsory misses. And we know compulsory misses, there's a mechanism called prefetching. And in fact, in x86, you can also do software prefetching. And there are 2 ways. One is that you can just use the GCC flag to prefetch, or you can manually insert code for that. So this is the version of the prefetch code that I wrote. And here I'm just like, this is like very not easy to understand because there are a lot of manipulation in pointers. However, on the same processor, it used to be 0.1 seconds, which is 10% of your, well, 5% of your execution time in doing matrix transpose. But right now, it can go to 0.07 if you do a good job in prefetching. However, this doesn't always work very well because like for other processors, if they already have a pretty smart prefetcher, you will see it's very limited effect. So what does that mean is that, okay, you can actually use prefetching to further reduce the compulsory misses, but also 2 things, because compulsory misses, they are already not a major. So you will see, even with the most optimized prefetcher, we can only reduce the execution time by 0.03, which is less significant than other stuff. So compulsory misses prefetching, I would say that's probably the least thing you want to do to improve the performance. Okay, so I know you are here for a reason. So first of all, here's the format of the midterm. So it's between between Monday, Friday next week, as long as you can find a slot from the website. And everything about scheduling, every test you're releasing, don't talk to me, talk to the testing center. If you need accommodation, you have to reserve a slot with them first. Then I can confirm that we can accommodate that. But without you making this reservation first, there's nothing I can do. And it's 80 minutes, closed everything. The calculator, you can only use the Python-based interface or the Java calculator that's embedded on the screen. If you don't know how to use that, you already missed the chance. And 15 multiple choice questions, each cost 3 points, and 3 assignment style free answer questions. And so these are the multiple choice questions that I grabbed from the slide for you to practice. And if you want to find the answer, you should review the slide that we have. And this is pretty similar to what we are going to test, but not exactly the same. And like sometimes I like to use multiple choice question to test your concepts. So these are the concepts that you should remind yourself. And we would definitely test you performance equation because I said there aren't that many equations you have to memorize, right? So what are the 3? Performance equation, mDOS law, and C equal to ABS, right? So the 3 free answer questions, performance equation, mDOS law, and C equal to ABS, as well as the cache simulation, right? It's not just C equal to ABS, but also cache simulation, right? So those are the questions that you might interact with, right? So again, reserve your slots as soon as possible. Check your grades on this particular website. Assignment 2 due tonight, and we still have a reading quiz due next Tuesday. And one more thing that the TA just reflect that, first of all, I want to let you guys know, as a student, you probably don't know, but all our TAs are now unionized. They cannot work over 10 hours per week. And for this class, we only have 43 students, which we only allow 10 hours per week TA time. So I want to say this has been changed in the past because previously over 35 students, you can get 20 hours of TA. But now, because the school tried to save money and because the union asked for salary increase and the school is a really bad employer in a way that, okay, if you ask for salary increase, we reduce the amount of employees that we have, right? So that's why you see on my website, I don't welcome people who enroll late because the way how they allocate the TA hours is based on the number of enrollments before the quarter begins. And we have been hurt a lot by that. But one thing I do want to mention is that a lot of you would like to directly contact the TA. And it turns out that those emails take the TA a lot of time, and the TA complains about that. So I want to make this super clear. We ask you to write email to CS203@itscalab.org instead of the TA's email address. So if you email directly to the TA has the right to reject, to refuse answering your question. Okay? Other than that, enjoy the rest of your day. I will see you next week.